Hello. So last video we have seen insertion in B plus tree. So this video we will see how basically deletion in B plus tree goes. Okay. So let us take a simple example now. So this is a B plus tree where I want to delete now here 32. So here I want to delete now 32 from given node. So if I look at in the given B plus tree, so node 32 over here, I can find that 32 is present basically here also, that is in index node also, and it is present in the data node also. So if you look at here carefully, this 32 which is present in data node, here in data node and here in index node. So what I'll do first of all, since that 32 actually an index node has been taken from a data node, first of all I'll take out this node away. I'll take out data node away. From given data node, I'll delete 32. So after deleting the 32, only remaining data nodes, the keys in given data node are 36 and 38. So these are the only two keys which will remain. Now, if I look at here, actually the required minimum number of keys are 2, and which is fulfilling by this particular node over here. Now, when I will look at the index node. Basically in index node there is nothing. So ideally in index node we are taking the minimum value from its right link. So from here minimum value is 36. So here basically I'll be taking now 36, and that's how deletion will go in this case. Okay, so let us look at now the next case. So after deleting the 32, the tree will look like this, as we already seen here, right? Now let's say in the given tree, let's say I want to now delete here 15. So I want to delete now 15. So if I look at in given B plus tree, 15 I will find at this point. Okay, again here now 15 is present in index node and it is also present in data node. So if I delete 15 from the given tree, so basically what will happen, this particular node. So in this node, if I remove 15, so this node will only contain now only one key, that is 16, and the minimum required number of keys are 2. So this node now will become a deficient because it is not fulfilling the definition of B plus tree of order 3. So what we will be doing here now, we will combine this 36 with its immediate sibling. So now here immediate sibling is what? 312. So we will bring 16 over here. Okay, and then we'll get a complete node of 3, 12 and 16. Now if you look at, okay, now this node at the data level is fulfilling the definition of a B plus tree. Okay, so B plus tree here is fulfilled at the data level, but what about the index level? Because here I have deleted 15, so index level 15 is also got removed here. So this node, it becomes now deficient. Now here it's just like the case of deleting a node from a B tree in horizontal nodes. You can look at here. Since I have removed here this 15, this node becomes deficient, right? So here at this level, this is a B tree of order 3 again. So minimum required number of keys in every node is 1. So try to understand very important difference here. When I say B plus tree of order 3, at the data level, it should have a minimum of 2 nodes. Minimum of 2 keys in every node. Whereas in case of the index node, that is horizontal nodes here, the minimum nodes will be 1. So it should fulfill the definition of a B tree of order 3. So when I define here a B plus tree of order 3, so that means at the index level it will have a minimum of m minus 1 nodes, m minus 1 by 2 nodes, m by 2 nodes, sorry, and here at this level, horizontal level, it should contain basically the number of nodes should be of a m by 2 minus 1, which is defining by a b tree over here. So now here we'll see now what to do now. So in this case, this node is deficient. This node, particular node, is now deficient. So what we'll do, we'll combine this node with its parent and with its another sibling. So after combining this, we will get now here 18, we'll get another node 36, and we will get another node 40. So they will join horizontally all together. Now since this is a B tree of order 3, so maximum number of keys in every node will be 2. So what we'll do here, we will shift that 36 at upper level, and here the resultant tree will look like this. So if you look at here a particular tree, you will find the resultant tree basically will be looking like this. So after deleting the 16, basically this 14 is joining here. Now the problem is that we are combining here 18, 36 and 40 at the same level. So here we are just like deleting the 15 from B tree. So what we'll do here now, this 18, 36 and 14 needs to be joined. So ideally now this 18 will come here, 36 will shift up, and 40 will come here. So if you look at here carefully, what has to be done now? This node 1830, it should shift at this point. So this 1830 will shift over here. So we'll get here 18 and 30. Now what about this 40 over here? So for this 40 will remain as it is, and this 36 will come here, 38 will come here, then 40 and 45 will come here. So that's how the deletion of 15 from above node will take place. So I'll repeat the process once again. What we have done are actually in this case, so ideally when I want to delete 16 from above tree, what we have done, since we have deleted a 16 over here, and since this 16 which is a part of index data level we have deleted, this 14 shifted here. Now there is nothing in this node, so only one data link is there, so that 14 automatically deleted. Now this node becomes deficient, so what we have done, we have taken out 18 down. Actually we have combined that this node plus this parent plus this node, and then we got 18, 36 and 40. But this is a B tree of order 3, so minimum number of required node here are 2. Sorry, maximum number of required node will be 2. So here there are 3 keys, 18, 36 and 40. So what we have done, we have shifted 36 at the upper level, 18 and 40 will divide it, that is 36 will become parent and 18 and 40 will become child at the B tree. And so this 80 and 30 will shift on this left side, and so we'll get here the resultant tree look like this. 80, 30 shifted here, 36, 38 is here, and 40, 45 is shifted over here. Right? Now let us delete 14 from this tree. So here if I delete 14, so if I try to delete 14 from here, so if I simply delete 14, it will not affect anything in the given tree, because by default it is fulfilling all the definitions of B plus tree. Let us go for the next deletion. So let us try to delete here 18. So here when I am just trying to delete now 18, so 18 is basically at this level. So 18 is a part of data node also, and it is a part of index node. So what will happen if I delete 18? So by default I'll delete from data and this node also. Now particularly here this node becomes a deficient because this node will contain here only 30, and then it is a B plus tree of order 3, so this will only contain 30. So ideally this node is deficient, so what I'll do, I will join this 30 at this line. So this 30 will come here. Now what will happen now at this point, this node is clearly defined, right? So this is fulfilling definition of B plus tree at data node. Abhi this node will not exist. This node will not exist. Because here basically this node is ideally not in existence. Only this node is in existence, which is containing 3, 12 and 30. Now here basically the problem is there at upper level. At this level the problem will occur because this node no key value, this node has a single key value, and this node has only one key value. So this is just like deleting a key from a B tree. So what we'll be doing now here, we will combine this node with its parent along with its sibling. So sibling is here 36 and 40. So what we'll be doing here, 36 and 40 will come together. So this is 36 and 36 will get joined with 40. So after joining this 36 with 40, it is still fulfilling the definition of a B tree, not a B plus. It is fulfilling the definition of B tree of order 3, right? That means it is fulfilling the index node definition of B plus tree of order 3, and it will have 3 links because number of keys are 2, so number of links will be 3, and we have 3 nodes, 1, 2 and 3. So one node will join at the left of 36, this node will join at the right of 36, and another node will join at the right of 40. So here this is already actually defined here. So here you will get the structure like this, and at the end the resultant answer will getting the final tree like this. So I'll draw here final tree. Here you will be basically getting a 36. So I'll write here 36, 40, and rest of the resultant 3 nodes will come at this position, whereas this upper part will not be in existence. Okay, so this is about deleting a node from the B plus tree. So let us try to look at the algorithm. So if you look at the algorithm here, remove the key from its leaf node. Let's say the first thing, because all the nodes in B plus tree, the data nodes are basically residing at leaf level. So as we know the definition of B plus tree, we know that all the nodes, that is data nodes, they are at the leaf level. Okay, so if you look at here now this algorithm, remove the key from leaf. So first of all I'll find out the key, I'll remove that key from leaf node. Then next thing, we'll try to find out after deleting that particular key whether it is fulfilling the definition of a B plus tree node or not. So if leaf node ends up with a fewer than L by 2 items, that means the underflow occurs. So meaning of this statement is that if I delete a particular key from a B plus tree node, then I'll just check it whether it is still fulfilling the definition of a B plus tree node or not, if I deleting a particular key from B plus tree. If it is underflow, that means it is not fulfilling the definition of a B plus tree node. What we'll do here, adopt the data from the neighbor and update the parent. So what we are doing, we are taking the data from the neighbor and will update the parent, because parent is obviously the index node, which is basically containing the minimum from its right link. Now, when can I adopt the data from neighbor? Only when neighbor contains the more than required number of keys. If it doesn't contains more than required number of keys, then what we'll do, we will delete that node and we'll merge our node with the neighbor. That's what we have done, right? And then if we check at the parent level whether it is fulfilling the definition of B plus tree data index node or not, which is contain m by 2 children or not. If not, then what we'll be basically doing here is we will do now adjustment at the internal node. So you can see here we will be doing basically the adjustment at the internal node level. So that means we'll do the same as the B plus tree case. So here, if the internal node underflow occurs, what we'll do, adapt from a neighbor and update the parent. If adoption from neighbor won't work, then again we'll go for merging with the neighbor. So this point 3 basically talks about the adjustment at the horizontal node, that is adjustment at the index node, whereas the point 2 was basically, it is basically just talking about the adjustment at the internal node. Then the next thing is here, if root ends up with only one child, then what we'll do, make the child as new root of the tree and propagate the keys up through the tree. So try to understand one point here. When actually we go for a deleting a node from a B plus tree, obviously we are deleting that node from the leaf level, because only data nodes are present at the leaf level. So that is the definition of B plus tree. Once we remove that node from the, or key from the B plus tree leaf node, we'll check out whether it is fulfilling the definition of B plus tree node or not. If not, we'll try to make it a B plus tree node, and then we'll propagate our problem or shift our problem of deletion to the upper level at the parent level. So that's how basically the deletion in B plus tree goes. So let us see some points about the B plus tree. So these are some very important points of the B plus tree which we need to discuss. So generally B plus tree, basically B plus tree required here actually propagation level deletion and insertion is expensive. So actually it is expensive for insertion and deletion because we propagate the problems at the upper level. Another thing, B plus tree deletion can cause a chip adoption or deletion, merging and propagation. So that means actually we have seen now deletion and insertion cases of B plus tree. So there are the problems of merging and propagating the problems at the upper level, or propagating the deletion at the upper level, right? So there is a case of adoption, expansion during insertion and deletion. Okay, so these are some very important point in the B plus tree. So generally when I say insertion or deletion from the B plus tree, they involves basically two operations. The first thing is basically merging. If merging doesn't work, we go for adopting. Okay, so there are multiple cases available which are already seen. To again, once I delete a key from B plus tree, how to make the resultant tree again as a B plus tree. Another very important point here is that B plus tree with m is equal to 3 and l is equal to x are called as a 2-3 trees. So why it is called as a 2-3 trees? Because the nodes can have 2 or 3 keys. Another case, B trees with m is equal to 4, l is equal to x are called as 2-3-4 trees, because nodes can have 2, 3 or 4 keys. So m is equal to 4 and l is equal to x. So when I say order 4, it will contain 2, 3 and 4 nodes in these different cases. Okay, so this is about the deleting a node from the B plus tree. Still, I insist, you should solve more examples on B plus tree, how to construct a B plus tree, how to insert a node into B plus tree, and how to remove a node from the B plus tree. Also, you can do a comparative study of B and B plus tree, because nowadays in most of the applications, especially in the databases, B and B plus tree are very much prominent, and they have been used at a higher level in the basically in the many databases at the backend level. Thank you so much.